Hello, class. This is Mr. Hart. And in this podcast, we want to start talking about rotational momentum. Okay. Up to this point, we've been talking solely about linear momentum, meaning objects moving in a straight line. But objects that are rotating also have momentum associated with them. Okay. In other words, an object that is spinning has a tendency to remain spinning. Okay. It carries its momentum as it spins. Okay. The fancy word for this in physics is angular momentum. And just like in linear momentum where it keeps moving until something hits it, same thing with rotation. A thing that is rotating is going to keep rotating until something slows it down, either through collision or friction or something like that. Okay. Now there's a lot of applications that come from angular momentum, and you probably have experienced a lot of these. Okay. One of these is a gyroscope. Okay. Now if you've never seen a gyroscope, it's very similar to a top. You just pull a little string and it causes this wheel in the center to spin. And then the gyroscope will just sit on the table and sit there, okay, similar to a top, okay. Well, why is that happening? Well, this wheel in the center just keeps rotating and rotating around, okay. It doesn't want to change the direction that it's spinning. So if the gyroscope is, sitting on the table straight up, okay, like this, so the wheel's spinning this way, okay, and it's going around, okay, it doesn't want to quit spinning in that direction. It doesn't want to lean like it is in this picture. Okay, it wants to keep its momentum in that direction. That's why tops and gyroscopes can stay up for so long, is because they have that rotational momentum, okay, going that direction. Another application that you probably know is with bicycle tires. Okay, now if you get a bicycle moving, right, that's what makes it easy to stay up on your bicycle. Because the wheels have their rotational momentum or angular momentum, they want to keep spinning in that direction. They don't want to lean left or right. Okay, they want to keep spinning in that direction. That's their angular momentum. Okay. Now there's a lot of weird properties that come with this. There's things like torque and other parts that cause this to keep its direction. We're not going to go into that. Just I want you to understand this main principle that an object's rotation wants to keep it rotating in that direction. Okay. In class, I actually have the students hold a bicycle tire by the axle. Okay. And if you've never done that before, it's kind of a weird sensation because if you want to move it, you can kind of feel a force, right, that resists your movement of the rotation other than the direction the bicycle wants to move. Because the tire is spinning like this, it doesn't want to move left or right. Okay. It will kind of resist that motion. It's kind of a weird sensation if you've never done it. So if you haven't, come talk to me and I'll do that demonstration for you. But anyways, again, angular momentum, it keeps rotating in that direction. Okay, it wants to keep rotating in that direction. Okay. Now, just like with linear momentum, angular momentum is conserved. So we have this version of angular conservation. Okay, so angular momentum is conserved in a closed system. Now, we have a little bit different definition, okay, because in this case, our angular momentum is defined by the radius squared, okay, of a mass, basically the distance from the center that the mass is located. So on a bicycle tire, it'd be the distance of the wheel, right, the radius of the wheel, okay, times the angular velocity, okay. So not just how fast it's moving, but more specifically how fast it's spinning, okay. How much angle is it spinning by in a given amount of time. Okay, so your initial radius and angular velocity equals your final radius and angular velocity. Okay, and the radius is squared. Okay, and at the moment I don't have any example problems for this, but you'll just take the distance to the mass, its angular velocity, then the distance that the mass decreases by, and then you'll get your new angular velocity. Okay. Let me give you some examples of when that might be useful. Okay, a common example is a merry-go-round. Okay, and if you've ever played on a merry-go-round, they're not as popular anymore because they're kind of a safety concern. Okay, but if you ever played on a merry-go-round and you get 3 kids on the outside, and then you move to the center, okay, then you'll notice that the merry-go-round is going to spin a lot faster. Why is that the case? It's because of that equation. Okay, so r squared initial omega initial equals r squared final omega final. Okay, so if everyone's a really far distance away, okay, if R is large, everyone's on the outside of the merry-go-round, then the omega is going to be small. But then if everyone rushes towards the center, okay, and the radius decreases, then guess what? The spin is going to increase. Okay, omega is going to go up. A funny story with this, this picture is of the Empower Playgrounds merry-go-round. When I was a student teacher, I had the guy that owns the company, he actually was willing to do a demonstration for us at the school, which was really cool. So he brought in one of the playgrounds and explained how they use the motor to generate electricity for these developing countries. So they have lamps and lights for doing homework for the kids in school and things like that. So it's a really cool program. And then after he explained everything, he let the kids play on the playground for a little bit, or the merry-go-round. And these are high schoolers, but they still wanted to play on the merry-go-round. And it must have been my, foolishness as a student teacher, but they convinced me to get on the merry-go-round. Okay, and I'm wearing, nice, black shoes. They're not very good for traction and things like that. They're very slippery on the bottom. And the students all had it in for me. They all started on the outside going pretty slow, and then they all rushed the center at the same time. Okay, so guess what happened, right? They all had a large radius to start, and then they decreased the radius, so omega went a lot faster, right? The spin went a lot faster. Now, if you're on the inside, that's not a problem, but I didn't know they were all rushing this, so I'm going on the outside, so I'm going a lot faster than everyone. My shoes slip from underneath me, and I'm basically holding on to the merry-go-round, kind of parallel to the ground, holding on, and eventually I let go and roll on the grass a couple of times. It was pretty funny. The kids enjoyed it. But I learned my lesson. Don't wear slippery shoes on a merry-go-round. And don't ever do anything your students tell you. That's the other lesson. But anyways, the point is, right, if you decrease that radius, the object's going to spin faster to conserve angular momentum. Another application of this is figure skating. If you've ever watched a figure skater do like a turn or a spin, they'll fold their arms in like this, right, and they'll start going super, super fast, and then when they need to slow down, they'll reach their arms out, okay, and they'll slow down and continue their routine. Why do they do that? Well, same idea. When they get into the spin, they start out slow, and then they'll decrease that initial radius, right? So they start out slow, then they'll bring their arms in, which will decrease the radius. So they'll spin a lot faster, okay? So omega goes up. Then when they need to slow down, they'll put their arms out as far as they can. So R goes up, and so what happens in return? The spin goes down so they can control themselves and continue their routine. If you haven't watched this video right here, I highly recommend it. It shows a figure skater doing a world record spin for speed. Reaches some ridiculous amounts. But again, conservation of momentum is why that works. All right, let's do one more application, and this has to do with spacecraft. Okay, now this is a true story. I don't know exactly what launch it was or what mission, but it was during the space years of the 60s, and if you remember back then, computers didn't run off of microprocessors and things like that we have nowadays. They used these huge tape reels, okay, to store data. So they launch off this spacecraft, and it's working just fine. It goes into the atmosphere, it goes into space, no problems, and it's heading towards its destination. And then like halfway through its destination, they start to notice that the rocket's not facing the right direction. It's kind of tilted its trajectory. And they're all confused, like, what the heck, we're in space. We haven't launched rockets or anything. How's this thing tilting? Okay, well, guess what? It had to do with those computers, because those computers had tape reels in them. Okay, now it wasn't a huge effect, but over the time, while it was collecting data, right, that tape reel, let me do this in a different color, that tape reel inside the rocket was rotating in this direction. Okay, now it's going around and around and around. Okay, and if initially nothing was rotating, by conservation of angular momentum, what does the rocket have to do? Well, guess what? It has to rotate in the other direction. So that wheel is spinning inside. It's rotating. To conserve the angular momentum, the rocket has to do the opposite effect. It won't do it as much because its radius is a lot larger and its mass is a lot larger, but it did cause that rotation to occur. So then for a while they still used those tape computers, they'd actually put a second disk on top that was just to balance out that effect. It just rotated the opposite direction. Didn't have any tape on it or anything. It just was to counterbalance the rotating effects of the computer. Okay, so pretty cool stuff. Angular momentum's pretty amazing. But just make sure you do the homework. Let me know if you have any questions, and thank you for watching.